Okay, so the screen is there. Okay. Okay, so we were discussing quotient spaces. So let me just recall what we were doing. So we were, so we have a, so we start here. Okay, let X be some normed linear space, and X naught is a subspace. Okay, then we consider this quotient. So this is all those equivalence classes with respect to some equivalence with X and X. So what are these? What is this equivalence class? It is just X is equivalent to Y if X minus Y is in the subspace X naught. Okay, and this is precisely equal to all those elements of the form X plus X naught. Okay, where X, I mean this may be same thing, but elements will look like this. Okay, X and X. This is linear algebra, and we okay. So this is the quotient space. Okay, I mean, last class, someone was asking about complement space and other things, but that's a different issue. But the point is, we want to see, we want to define quotient space means whatever we have two structures on this. One is a norm structure, which is a topological structure. The other one is an algebraic structure. So this is the algebraic quotient where we want to define a norm, which is a well-defined norm. I mean, whatever we talk about topological quotient, that should be the norm. Okay, I mean, whatever quotient metric or something. So that should be the metric. Or, I mean, we should define a norm so that we should get the topological quotient as well as the vector space quotient. Then you can ask the questions whether it is same as the complement or something. That's a different question. So we cannot define through that. Okay, that is not the quotient space. This is the quotient space, and the where we want to define the norm. So here the right, I mean, what is the right norm when you want to define a quotient in a metric space or a topological space with respect to some set? You will treat that set as a point, single point, and then you will talk about. So it will be like that X naught will become a single point. I mean, which we should. I mean, in this case, it's a zero element. I mean, it's also a vector space. So we have to consider treat this as a vector space also. So as a vector space, this X naught is corresponds to the zero element. So norm of that X naught should be zero. That's the number one. And another then we should, I mean, then for any other vector in this quotient space, the distance should be the actual distance from the, I mean, so whenever we have a closed set or any, I mean, then we can define a distance between some element and the set. Okay, so that's what we should be, and that is precisely equal to this. So the for any quotient norm of any this X equal to, you can even say, I mean, it is infimum of norm of X plus X naught with X naught is in X naught. So this is the right definition, because this is the quotient, this gives the quotient metric, and this is the defined on the quotient space. So algebraically, topologically, this is the right definition. Okay. Then you can ask the question whether complement spaces, I mean, when you take the complement, whether you will have isomorphism between the complement spaces and this, which is true only if it is Hilbert space. Otherwise, it's not true. So we will try to see that. Okay, so this is also equal to infimum of all those y in X. Okay, norm Y. Okay, you can even say that. It's the same thing. All, I mean, everything in this Y, everything in the equivalence class will look like this. So, I mean, this is precisely the equivalence class. Or this is also, you can say that this is, I mean, this is same, something like this. Okay, that's what we want to say. So, this is the definition of this norm. So, I think we have verified it's a norm. So, this is a, maybe I will call it norm naught. Okay. So, to say that it's a quotient norm, then this is a norm on this quotient space. I mean, this is a semi-norm on this quotient space. It's not a norm. It will be a norm if X naught is closed. So it is clear it's a semi-norm. I think I have verified last class. I mean, okay, you can even say that if you take alpha X, okay, norm of this is equal to infimum of X naught in X, okay, alpha X plus some X naught. This is same as infimum of x naught in x. You can take the alpha out, mod alpha. Assume that alpha is not equal to 0. Okay, alpha equal to 0 is clear. I mean, it will be the norm will be 0. So that is clear. So assume alpha not equal to 0. Then this will become x plus x naught by alpha. Okay. But then this is same as infimum because it's a vector space. X naught is a vector space. X naught by alpha, when you when you vary it over all, all x naught, x naught in x naught, this will also vary over all throughout the whole vector space x naught. So this is same as this. Okay, so this is equal to mod alpha times norm x. Norm x, this x equals class x. Maybe there's a not here, there's a not here. If I miss it, understand that it is the quotient norm. So similarly, I don't know whether this I verified, this plus this. Okay, you take two of them, and that is going to be same as x plus y, say x naught, same as this naught. That is equal to infimum of x naught in x naught, x plus x naught, x plus y plus x naught, x plus y plus x naught. But then you can write it as x naught plus y naught for some other y naught also. You can write it like this. Okay? I mean, this is the same infimum. Okay, this has to be equal to x plus y plus x naught, this infimum. Okay, infimum of x naught in x naught. Okay, that's what this should be. But then you can write it like this. It will be the same infimum. You can vary it over this. So then this is less than or equal to the usual triangle inequality. Using that, you will get infimum of x naught in x naught, x plus x naught, plus infimum of y naught in y naught, y plus y naught. Okay, this is equal to okay. I went fast. It's I think it's clear. So I think we have already verified that this is a norm. So for x naught in x naught, this x naught, which is full of whole of x naught equal to 0, that is clear because the infimum will be attained at 0. On the other hand, if otherwise it's not true, it's clear because you can have a, if it is not closed, there is an element for which something from x naught, from this x naught will converge. So if x naught is closed, then if this norm is equal to 0, then there exists some, call it maybe xn contained in x naught, such that norm x plus xn is less than 1 by n or whatever. Okay, so this implies x plus xn goes to 0, xn goes to minus x. So because since x naught is closed, x is in x naught. Okay. Okay, so we have verified that it is a norm. Okay, so what we have is a norm when x naught is closed. Okay, so that is one thing. So someone was asking about complements. We will be doing Hilbert spaces. There it is true that if, there is a unique complement called orthogonal complement, which you must have seen in vector spaces, at least finite dimensional one, inner product spaces. There you have an orthogonal complement. Then it is indeed true. So, for example, if you have R2, okay, see there is something called, I want to say true Banach space. See, you will treat two sets as same set if there is a bijection between them. Unless you specify a property among those elements, there is no difference between any two sets with the same cardinality. Similarly, if you have a group, or if you have any object, algebraic object or topological object, then if you have an isomorphism between them, which preserves all the structure, okay, then you treat it as same elements. You can identify those elements. Similarly, we identify two Banach spaces. So if x, y are Banach spaces or non-linear space,
Why is he talking like this?
Yes. If xy are non-linear space, then we identify, then X is isometric, is isometrically isomorphic. Okay. Isometrically isomorphic. See, usually vector spaces, we identify two vector spaces if there is a linear map from X to Y, which preserves the vector space structure. So, which is linear and it's also bijective. But when they are topological spaces, we need them to be homeomorphic. Okay, the T should be continuous, T inverse should be continuous. But here we want them to preserve the norm also. See, there may be some isomorphism, continuous isomorphism. For example, all finite dimensional spaces. You can take Rn or Cn. You can define L2 metric and LP metric, LP norm and L2 norm. They are different as Banach spaces, but there is a someone is saying something. Then then any map is continuous. So you always have the identity is an isomorphism, which is also T and T inverse are continuous. But then as Banach space, they are different. But you need a map which preserves the norm. Okay, so if there exists a T from X to Y, which is linear, bijection, and norm Tx equal to X. Okay, so if the norm should also be preserved. Okay, so in that way, if we have a X and a X naught contained in X, okay, closed. Okay, if X is also a Hilbert space, I will talk about it later. Okay, then X by X naught is isometrically isomorphic to X naught per. This is not true if it is a Banach space. Okay, so algebraically there will be a complement, but the complement may not be a Banach space. Usually, that is one thing. In fact, there is a theorem, very deep theorem, saying that, I mean, in fact, there is a deep theorem. If you have many Banach space, in all these LP spaces, everywhere it's true. It's true in Banach space also. If any Banach space, if you have, there will be exist a subspace whose which cannot be complemented. Okay, in the Banach space sense. Okay, so because of that, and it will not say, you can see this example. For example, if you have take R2, for example, R2 or C2, I mean, whichever you want to consider R2, since we want to view it, let us call it R2. Then this is one subspace. Let us call this subspace as X naught. Okay, our X is equal to R2. Okay, then as a Hilbert space, X naught, this is the Y axis. Okay, call this Y naught. Okay, then that is isomorphic to Y naught as a Hilbert space. If you take it, if you consider the X by X naught, I mean, with respect to the 2 metric, with respect to the 2 norm, then this X by X quotiented with X naught is isomorphic to this Y naught. Okay. On the other hand, if you take this line, for example, okay, if you take this line, then, so this is complemented subspace. Okay, you call it Z or something. Then Z plus X naught, Z plus X naught equal to X. Okay, but then X by X naught is not isometrically isomorphic to Z. That's because if you, I mean, you should have an isomorphism. I mean, you cannot. No, you can have an isometric isomorphism. You can have something. So that is not the right thing. What I'm saying is not correct. There will be an isomorphism, but that's not the natural isomorphism. How will you identify that? You will find some isomorphism. Now it can be equivalent. So what I thought was, if you take, see, in this subspace, in this x-axis, y-axis, the distance from this space to here is precisely attained at 0. But here it will be attained at some point here, right? The minimum distance will be attained at some point, not at 0. So if you use precisely that definition, the norm here, then, I mean, if you take the equivalence class to that, if you take, this Z equivalence class to Z, there will be a Z. If you take an element in Z in Z, then you take the Z equivalence class going to this Z. That will not be an isometry. Okay, but you can find different isometry. But in general, anyway, every Banach space cannot be complemented. That's true. So this complement is not a nice idea. Okay, but it works in Hilbert spaces. Otherwise, it will not work. Okay. Anyway, let us stop this. Unless you have some questions. You have any question?
Sir, can you give some reference to that theorem which you were referring?
What is the theorem? Now, that is in some paper. You have to search. You search in the internet, you will find it out. I don't.
What shall I exactly search? Can you state it once again, please?
Quotient space, complementary space. You will get a series of paper. I can. I have to search also. So I think the person name starts in T or something. T some. Now you search for complementary subspace and quotient space. You will get something.
Okay, sir.
Okay. Yeah. This complementary subspace, existence of that, these are all very interesting problem in Banach space theory. For example, if you take L infinity, small L infinity, ball bounded sequence, and you take sequences convergent sequence, or converging to zero, the C0, that's a bounded sequence. So, for example, if you take C0 is always a nice example. Consider C0. This is all sequence xn converging to zero contained in L infinity. Then this is not complemented. The proof is not easy. Proof is easy, I think, but you have to consider a few things. Anyway, that's not the point. But this is not complemented. Okay. So in fact, there exists in all Banach space, there exists some subspace which cannot be complemented unless it's a Hilbert space. Okay. So that's the theorem. Anyway, so let us do something else. Yeah. So next, I want to prove the following proposition. I want to prove that the quotient map. So we have the quotient map. So we'll define pi from x by x naught to, x to x by x naught, x going to this equivalence class. This is what is called the quotient map. Okay, then the proposition is pi is continuous. Okay, this is just clear because if pi is continuous, we want to prove. Suppose xn is some sequence contained in x, xn converges to x, then you want to consider this xn minus x. Okay, in the norm, quotient norm, whether it converges is the question. So this is same as norm xn minus x. Okay. Now this is equal to infimum of infimum of but this is smaller than norm xn minus x naught. Okay, which goes to 0. That's all. Okay. So this is direct. There is really nothing in this. Okay. It is in fact contractive. We will see that it norm is less than or equal to 1. It is in fact true that pi of x, this norm, is less than or equal to norm x. Okay. Indeed. This will imply continuity. That's what we are going to see immediately. Most of you may know it. In fact, I have done it in my analysis course, that bounded maps are continuous maps. So because of that, it will follow that it's continuous. Anyway, that's the next thing. Now we want to prove. So next proposition. If x naught contained in x is closed and x is complete, then the quotient is also complete. Okay. Okay, that's the next thing I want to do. Okay. Okay, proof. Okay, so what do we have to do? We have to prove that x, we assume that x is x not everything is complete, then the quotient space is complete. So we want to take a Cauchy sequence, and no, we want to use our criterion. We have our criterion that a Banach space is complete if and only if every absolutely convergent sequence actually absolutely convergent series actually converges. Okay, so that's what we want to prove. So suppose that this is enough to prove the following. Suppose xn, this is a sequence, a series contained in the quotient space, such that summation norm of this xn with respect to the quotient norm is finite. Okay, and it is enough to prove. To prove the quotient space is complete, it is enough to prove this actually the series converges. Okay. Enough to prove this series converges. Okay, converges in this Banach space. Sorry, in this non-linear space. Okay, it's enough to prove this. Okay, so how do we prove that? Okay, so we want to find a limit for this. Okay, now we take this series. We corresponding to this series, we are given a series in this quotient space. Now we take a series in the original space, in this bigger space x. Okay, and that will, because that is a Banach space, there it will exist a limit, and we will bring it here. Okay, then we will take the quotient thing and do that. So what should we do? So, but it's not. But this is an equivalence class. This is not a single element. So its pre-image will not be one. So we do the following. We want to do it a bit carefully. Okay, choose, call it yn in x naught, such that norm of this xn naught plus 1 by n, so not 1 by n, 1 by 2 power n, because we want to sum it, 1 by 2 power n is greater than or equal to x plus xn plus yn. This is possible because infimum of these kind of elements, infimum of this kind of thing is what is that now. So because of that, by the definition of infimum, we can get this. Okay, this is true. Now summation norm xn plus yn. Okay, this is n equal to 1 to infinity. This is less than or equal to summation norm of this xn naught plus 1 by 2 power n is finite. Okay, so this is absolutely convergent. This series is absolutely convergent. Okay, this series is absolutely convergent. So since x is a Banach space, the earlier criterion says that there exists a x in x, or x is enough, x in h such that summation xn plus yn n equal to 1 to infinity equal to that x. Okay, the limit for this series exists, so I write it as this. Okay, now our claim is summation n equal to 1 to infinity this xn converges to, the series, whatever it means, converges to this x. Okay, so to find that, we have to find the norm of this. So we have to consider this summation n equal to 1 to k or n xk, okay, minus x. Okay, this is equal to the norm not. We want to show that this goes to 0. That's what we want to show. We want to prove that this converges to this. So we want to prove that this goes to 0. That's what we want to do. Okay. Now this is equal to infimum of, I will use the notation y because that's what will y in x naught. Summation n equal to 1 to infinity, 1 to n xk. This should be k, I'm sorry. This is also k. Okay, xk minus x, I'm sorry, there is no equivalence class. Minus x plus some y, right? This is just the, I have just written the definition of the norm. Okay, this is the definition of the norm. So this in particular, you can put, I mean, if you substitute anything for y from this x naught, then this will be less than that, right? So I will substitute the following. So this is less than or equal to, because that is the infimum, summation k equal to 1 to n xk minus x plus summation k equal to 1 to n yk. You can just put it. You can put anything. Instead of y, I am putting summation yk. Okay. So now this is equal to summation k equal to 1 to n xk plus yk minus x. Okay, this goes to 0. Okay, so we improve. It's fine. Okay. I assume it's fine with everyone. Okay. Okay, so you have to stop me because I don't see anyone's face. I am not able to see whether it is fine or not. I assume it's all trivial for you, so I have done it. Okay, so then, okay, then I want to give an assignment. Okay, this is the first assignment in this Banach space theory. Okay, you collect all these things, and at some when some point comes, you submit everything after some time. I will announce it later, but you can start writing and storing it as a file. So assignment 1, this is just the converse kind of thing I want to do. If x naught contained in x and x by x naught are complete, I'm not saying it, I mean x naught is closed is not enough because x may not, I'm not assuming x is complete, so I have to say it is complete. Okay, are complete. Okay, then x is complete. Okay, I will give you the proof orally. So you want to prove x is complete. Okay, so you can use the Cauchy sequence. You need not do. You can try anything you want. Okay, so I will just try the proof now orally. So you want to prove x is complete. So you take a Cauchy sequence in that. Okay, then you project it into this quotient space. Okay, since the quotient space is complete, so if you have a sequence, so I will write it and erase it. If you have an xn sequence contained in this a Cauchy, then you can project it. You can consider pi of xn. Okay, so this will also be Cauchy because the quotient norm is contractive, we have seen. So this is also Cauchy. So there will exist a limit in this. So say some y or something. But then xn may not converge to y, but there will exist, you have to prove there exists some yn in this x naught such that xn plus yn will converge to that y. What? This xn may not converges, but there exists some xn will, so that this will converge to y. Okay. Now you should prove yn converges. Yn is Cauchy, and you have to find a limit or something. Then using that, you have to prove this. Okay. So I have given. I mean, I've told you the idea. So let me erase this. Okay. So this is the assignment. Okay, so we have talked about complement. It's always, I mean, in vector space wise, this is always true. Okay, notice this is true. I mean, this is just linear algebra. If you have any E contained in X naught, then not X naught. What I have written. No, if you have some, that statement is not correct. I think the right statement is so if you have any E contained in X, okay, then pi inverse of this equivalent E, I think is equal to E plus X naught, right? Is it right? So this is the proposition. If you have a X naught, if you have X naught, Y naught contained in X, X naught is closed, okay, and Y naught is finite dimensional. See, if you take two close Banach subspaces, okay, then you consider the plus, then that will not be, need not be closed again, okay. But then here X naught plus Y naught is closed. One of them is finite dimensional, then this is closed. So proof. So you consider X naught is closed, so you consider X by X naught. In this, you consider this image of Y naught and bring it back. Then pi of Y naught contained in X by X naught is finite dimensional. And Y naught is finite dimensional. We have assumed Y naught is finite dimensional. Then you apply the quotient map and you bring, I mean, take it into X by X quotiented with X naught. Then that is also finite dimensional. That is just clear because if you E1 up to En is a basis for Y naught, then this quotient 1, whatever it is, you may repeat it, doesn't matter. Okay, is a basis for pi of Y naught. Okay. Now you bring this, which is equal to X naught plus Y naught. Okay, by whatever. This is just algebra. But since this pi is, no, this is finite dimensional, so closed. I mean, this pi of Y naught is finite dimensional. Any finite dimensional space is closed. Okay, and hence closed. It's finite dimensional and hence closed. Okay. So since pi of Y naught is closed, this is closed, and you are taking pi is continuous and pi is continuous. We have proved that pi is continuous. This implies this inverse image of closed set is closed. This implies X naught plus Y naught is closed. Okay.
The equivalence classes of EIs would just generate pi of Y naught, right?
Equivalence class of EI generate
Pi of Y naught. You can't say that it would be a basis.
Yeah, it's not a basis. Sorry, it generates. Correct. That's what I wanted to say. I said even it may even repeat. So yeah, that may not be linearly independent. This generate. Yes. Correct. Correct. That's the right statement. Correct. They generate this pi of Y naught, so it has to be finite dimensional. So since it is finite dimensional, it is closed. You bring it back, and since pi is continuous, that is to close. This also implies that any finite dimensional subspace can be complemented. Okay, that's what this says. Anyway. So this is another assignment I want to give. So we want to talk about separability. I believe you must have talked about separability already. I mean, I assume that examples of Banach spaces. Example, you know this L infinity is not separable. All of you know this? Yes or no?
Yes.
So, shall I assume everyone is saying yes? I mean, this is just you take all this, let S equal to all those sets. Xn with Xn is in 0 or 1. Okay. Plus whatever. You take any two elements. Then the distance between L infinite distance between them will be equal to 1. Okay. Then if they are not equal, then the distance between any two elements in S is 1. Okay. But then there are uncountably many of them, and they are separated by distance. So that this cannot have a countable dense subset. L infinity is not separable. On the other hand, C0, all those xn converges to 0 with L infinity norm. Okay, this L infinity norm, this you consider a subspace of L infinity is separable. Okay, but then L infinity quotiented with C naught will not be separable because of the following reason. So why is this separable? That's because it has a, I mean, this has a L infinity does not have a basis. What do we mean by basis? There is something called shorter basis. I mean, what is the spelling? So definition. Yes, set yes contained in S or E. Let's say E contained in X is a shorter basis. I don't know spell. I think the spelling is correct. Okay, if you correct me if I'm wrong. It's a shorter basis. If span, you take the span of E. So this is just the algebraic span. Then you take the closure that is equal to X. Okay. Usually we call something as a basis if it is an algebraic basis. Span of them finite linear combination is supposed to be equal to X. Then I mean there is no topology, so you cannot talk about infinite sum. So you take this finite linear combination and then close it. Okay. So then this is called this is not shorter basis. I mean a linearly independent set. A linearly independent set, independent E, okay, contained in that is a shorter basis if it generates in this sense. Usually we say something generates if the span of that equal to X. But if the span closure is equal to X, then that's called a different kind of basis. Okay. So C0 has a basis like that. You take Xn, you take all those En. This is a sequence Xn with Xn equal to 1. I mean xk maybe xn equal to 1 and xk equal to 0 for all k not equal to n. Okay. Then this En is a shorter basis for that. It's shorter basis for C naught. You can take the linear combination and then if you take the closure, L infinity closure, then that is C naught. That will not happen in L infinity. Here the point is, so this is just an exercise. Okay, this is an exercise. You check. Just write it anyway. I will ask you to prove C0. I mean, I will ask someone to present the C naught, the dual of that, and consider this. So there it will be needed. You take this kind of element. I mean, you take the sequence with finite. I mean, sequences with non-zero element only at finitely many points and zero everywhere else. Such sequences are dense in C0. They are dense in any LP also. In fact, all this En, I mean, you can take the span of this. Okay, what is the span of this En? En equal to all those sequences Xn, such that Xn not equal to 0, only finitely many. Finitely many. Okay, at finitely many points. Okay, now this span, so you call this as E. Okay, this is just a set. I mean, you call. I mean, the earlier I called something E. This is a different E. Okay, maybe call it as yes. Okay. Yes. Then this S is contained in all LP, and this is just dense there. Dense. You can approximate because all those LP spaces, it will become zero. I mean, the tail part will be zero. So you have to use that and prove this. Maybe I give this also an assignment. Okay. So this is the assignment. So this is the, so you use this fact to prove the assignment, following assignment. Assignment 2, all LP spaces, LP P less than infinity, greater than or equal to 1 are separable. Okay, this is assignment number 1. Assignment 3, if X is separable, this is easy. Then X by X naught is separable. Okay. Then the fourth assignment is if X by X naught and X naught separable, then X is separable. Okay. Just to work with all the countable dense set. I mean, you have to take a countable dense set here, then you have a countable dense set here, and you take the sum of them and you have to show that that is dense here. It's easy. Okay. So these 3 as assignment. Okay. I have already proved what is called an isometry. Now let us see some examples of quotient spaces. For example, let C equal to all convergence sequence. Okay. Xn converges. Okay. And C naught equal to all those sequences which converge to 0. Then C by C naught. See, C will look like any sequence, any Xn in C will look like Xn. I mean, some Xn, say Xn converges to X. Okay, then Xn minus X. Okay, then there is a constant sequence. Okay, right? So in a sense, this will look like, I mean, this is not the usual direction. This will look like you can show that C by C naught equal to is isomorphic to C. Okay, I will show something stronger than this. This is this example. Let us consider this example. C01. Let X equal to C01. Okay, and X naught equal to all those F in C01. F of 0 equals 0. Okay. Then I want to say that the X quotiented with X naught is complex numbers. I mean, the proof is the proof of example 1 is similar to this. Okay, so this I will go through in detail. So I want to show that then X quotiented with X naught is isometrically isomorphic to C. Okay, so I want to write the isomorphism, show that it's a bijection, it's a linear, and it is isometrically isomorphic to this. So how do we do that? So if we have any f in X, f in any continuous function, then f minus f naught, this is a constant function. Okay, I mean, when I say just constant, this is this plus f of naught equal to f. Okay, this is in X naught. Okay, and this is a number in C. This is a function, but constant function C. Okay, everything will look like this. Now define a map. Define a T from X naught to C by f. I mean, here you will have a f going to f of f of 0. So first thing is t is well defined. That is clear. If you have f equivalent to g, okay, that means f minus g is in x naught. So f minus g of 0 is 0. This implies f of 0 equal to g of 0. So t is well defined. Okay. So everything in this equivalence class go to the same element, right? And clearly t is linear. I mean, if you have linear, and t is also a bijection. That is, if t of f equal to t of some g, okay, that is f of 0 equal to g of 0, okay, then f minus g of 0 is 0. This implies f is equivalent to g, okay, right? So okay, and t is on to, t is 1 1, t is on to. That's because if lambda is in C, then I mean, you just take any function. You can just take the constant function itself. Okay, you can take any, then for take any fn. Goes to lambda. Okay, right? You can just add it and you will get it. So only thing I have to prove is it's isometric. In C there is only one norm. It's just the modulus norm. Okay, so I want to prove that it's isometric. So norm of f equal to infimum of norm of norm of G. G is in the equivalence class F, right? Okay. This is the definition of the norm. And norm of G infinity. Okay. Notice that norm of G infinity will be greater than or equal to G of 0. Okay, because this is just a supremum norm. So it will be greater than G infinity. On the other hand, there will be the constant function is there. On the other hand, this G of 0 constant function, the constant function G of 0 is in this. Sorry. So I mean, I should say f, sorry. G of 0, which is equal to f of 0, okay? Because they are in the same equivalence class. F of 0, this constant function is in this equivalence class f, okay? So that the infimum is attained. So because of that, this is equal to f of 0. Okay? So I proved that the norm is in the mod of f of 0, sorry. So I have proved that the norm is exactly equal to modulus. So these things proves that if you quotient this C01 with all these functions taking value 0 at 0, you get complex numbers. It's isometrically isomorphic to the complex numbers. If you have any questions regarding this, you can ask me. You want to show, if you show, let me see what, is there anything else I have to do? That's all. Okay. What's the time? 5:52. Oh my God. I've taken a lot of time for this. Okay. So any question? I think it's all clear, crystal clear. Okay.
I had a question in the assignment problems.
Yeah, ask me.
So in all of them, we assume that x and x naught are non-linear spaces, and in the last three, do we assume they're complete?
The last separability.
Like, yeah, separability problems. Do we assume that they're Banach spaces?
Completeness. Yeah. I mean, you always assume x naught is closed. Completeness is not related. I don't see why that is.
Okay.
Yeah, that's not related. And in the assignment involving completeness, it's very clearly mentioned. So other things you have to.
So in all of them, we just have that X and X naught are non-linear spaces.
Yeah, and X naught is closed inside. I mean, to define the quotient space, quotient non-linear space, you need X naught to be closed. Okay, right. Okay, so let us stop discussing this quotient space. Maybe we'll come back to that later if needed. So let us do something. I mean, these are all simple things again. We want to talk about continuity. As I've already said, we want to talk about morphisms of our Banach spaces. So morphisms of vector spaces are linear space. Okay, linearity is the structure. So we would like our functions to preserve the structure. So lines should be taken to line. That's what it means by a map is linear. Okay, so you know what is linear map. So let me just recall it. T from x to y. X and y are non-linear space. It's linear if alpha x plus y equal to alpha times tx plus ty. Right. This is what is called linear. Okay. In finite dimensional, linear maps are automatically continuous. So infinite dimensional, that will not be the case. So for that, I assume you know this already because in my course I went through all these things. So and it's also easy, so I go a bit fast, and I want to anyway finish this today. So the following proposition: T is a linear map from x to y is linear. Okay, then the following are equivalent. This is my notation for following are equivalent. One, T is uniformly continuous. Okay, two, which of course implies T is continuous. Okay, three, T is continuous at some point x naught in y x. 4, this is equivalent to saying T is continuous at 0. 5, this is the final point. T is bounded. When we say bounded, it's not bounded as a function. It means it satisfies this. I mean, any linear map will not be bounded, of course. You can take x times something, k times that, and you will get any. I mean, the norm will go beyond any number, any m. So this is less than or equal to some k times norm x. That is, there exists k greater than 0 such that this happens. Okay. There exists a k greater than 0 such that norm tx is less than or equal to k times norm x. For all, this should be for all x. Okay. So this is the boundedness we want to use. So of course, 1 implies 2, implies 3, implies 4, implies 5. It's all clear. So no, not 4 implies 5 is not clear. T is uniformly continuous, implies continuity, implies continuous at some point, implies continuous at 0. So now from continuous at 0, we want to prove that it's bounded. So 4 implies 5. That's what we want to prove. So that is clear. We want to prove, suppose 5 is not satisfied, we will prove 4 is not satisfied. Okay, so suppose T is not bounded, okay, that is 5 is not satisfied, then we want to get a contradiction. Okay, T is not bounded means there does not exist a uniform K like that. Okay, that means there exists. So what is the? I mean, we want to so we have this statement, which is we have the statement. We want to negate this statement. Okay, we want to what is the opposite of the negation of this statement? The negation of there should exist a k such that norm tx is less than or equal to k times norm x for all x. So negation of this is for every k there should exist some x such that this inequality is violated. Okay, so t is not bounded. That is, so let us not worry about every k. In particular, for every n, small n in n, maybe capital N if you want, n in n, there exists a xn in x such that this inequality is violated. That is, txn is greater than or equal to n times norm xn, right? So this implies you can bring this number here, t xn divided by n times norm xn. Okay, I mean, I'm just still writing it like this, is less than, sorry, this is greater than n, greater than 1. Okay. Okay, but then this is a linear map. So this is equal to T of xn by n times norm xn. Okay, is greater than or equal to 1. This is equal to that. Because it's a linear map, I can take the constant inside. Now this xn by norm xn, this has norm 1, equal to 1. Hence, xn by n times norm xn goes to 0. But you call it yn. T of yn does not go to 0. Okay, so 4 is violated. Okay. Okay, so 4 implies 5 is true. If 5 is not true, then 4 is not true. Now 5 implies uniform continuous is clear. 5. Then for all x and y in x, norm tx minus ty equal to norm of t of x minus y. Because it's linear, that is less than or equal to k times norm of x minus y. This implies uniform continuity. Okay, that is clear. Is clear to everybody? It implies uniform continuity. Given an epsilon greater than 0, you consider the delta, which is epsilon by k. Then given any point, you can choose the delta uniformly for every x. You can take an open ball around this x, which is epsilon by k. Then when some z is in this open ball around that, some y is in that open ball around that, then that will imply that norm tx minus y is tx minus y, tx minus ty, norm of that is less than or equal to epsilon. Okay, go through the definition of uniform continuity, you will get it. Okay, so we have proved this. So this implies 1. Okay, so we verified all the condition of boundedness, right? So I assume it's clear to everybody. If not, you ask me. Okay, so boundedness, linear map bound. So I have to prove. I just want to prove only one thing. So I have 15 minutes more. I think I can do that. So then we will consider example in the next class, some examples of operators. So before that, I want to consider the whole operator as a whole collection. Okay, now you define the following. Define for t from x to y, linear and bounded linear map. Okay, or maybe, I mean, let me just, okay, let it be. I will just want to let xy be non-linear space. Okay, then b of xy equal to all t from x to y, linear, bounded and bounded. Okay, all bounded linear map, I denote it like this. So for t in bxy, define norm t equal to, I want to take the infimum of those, okay, or I will define in the following way. Supremum of norm x less than or equal to 1, norm tx. Okay, this I call it as norm t. Then if we define norm t like this, then norm tx for any norm tx by x, we just notice that x by norm x is equal to norm t of x by norm x. This has norm equal to 1, so this is equal to norm t. This is equal to norm t. Okay, this implies tx is less than or equal to, so this norm t is a k which satisfies that. Okay, I want to show that norm t is the infimum of that. Okay, so this is the claim. The claim is norm t, which we have defined like this. Okay, which we have defined like this is equal to supremum of norm x equal to 1 norm tx. This is one thing. which is also equal to infimum of all k greater than 0 such that norm tx is less than or equal to k times norm x. Okay. This is the smallest k which satisfies this condition. We have shown that norm t satisfies this condition here. Okay, we have shown this. We want to show that norm t is the infimum, it's the minimum k which satisfies that condition. So this statement is, clearly supremum of norm tx over norm x equal to 1 is less than or equal to supremum of norm tx, which norm x less than or equal to 1, because it's a supremum over a bigger set. That's a supremum over bigger set. On the other hand, if some x norm x is less than 1, okay, then x by norm x has norm equal to 1, and norm of tx by norm x, okay, this will be greater than norm tx, right? Because norm x is less than 1. So if you want to take the supremum here, if you want to take some norm tx here, there exists some element in this collection. I'm pointing here, but I cannot show it here. The pointer will not come. There is no pointer here. I'm saying that if you want to take the supremum here in this set, okay. But if you take some element which is not here, then there exists some element for this norm tx is greater than this. That's what this says. So this supremum, this implies whatever you have noticed implies that this supremum norm x equal to 1 is greater than or equal to supremum of norm x less than or equal to 1 norm tx. Okay, so they are equal. So whatever the first statement is clear, that statement is true. Now we want to talk about this infimum. That's also clear. That's also very easy. Why is that true? First thing is norm t satisfies this. Okay, so since norm t satisfies this, so let us call this infimum to be k naught. Okay, let this be k naught. Okay, norm t satisfies norm tx is less than or equal to norm t times norm x, that k naught is less than norm t. Okay. On the other hand, norm tx for norm x equal to 1, norm x less than or equal to 1, or norm x equal to 1, norm tx is less than that k naught. This is true for if you have a k which satisfies norm k times x, then norm x equal to 1. So this will go away. That is smaller than k. The infimum of k is that k naught. Okay, so it will be smaller than k naught. Okay, so this implies norm t is less than or equal to k naught. This is the supremum over all these things. Okay, supremum is also less than or equal to k naught. So this is easy. So I have proved that. Okay, so this is also proved. This where is the infimum? This is equal to this infimum. Is it okay if I go like this, fast, like this? Okay. These are all very easy, but if someone really seeing this for the first time, if they have some problem, you have to tell me. Okay. So now I want to, so with this norm, so this is the norm on this first thing is proposition B of xy is a normed linear space with respect to this norm. This is a norm on this. Okay. And B of xy is complete if y is complete. We don't care about the x. Y is complete, that's also complete. Okay. So proof that the norm is clear. First thing, if 0 has 0 norm, of course, that is clear. If norm t equals 0, then supremum of norm tx, norm x smaller than or equal to 1 is 0. So norm tx equals 0 for all norm x less than or equal to 1. But then for anything, any x, then for any x tx by norm x, as you can do, equal to 0 for all x in x. Okay, this implies you can take the norm x out. I mean, this is the Banach space norm. You can take the norm x out. This implies tx equal to 0. Norm tx equal to 0. This implies the Banach space satisfies the faithful condition. So this implies tx equal to 0. As a vector tx equal to 0, this is the number which is equal to 0. Okay, so this falls. So the positivity condition is satisfied. Then alpha times norm t equal to the supremum of alpha times tx norm dx norm x less than or equal to 1. Okay, then you can take the norm. I mean, this is just supremum of mod alpha times norm tx. You can take the alpha out. Okay, so let me not do it. This is equal to norm t. And similarly, if you take tx plus sx, this is less than or equal to tx plus sx. So when you want to take the supremum here, then you can, this is true for all of them. So this is less than or equal to norm t plus norm s. For norm x less than or equal to 1. For norm x less than or equal to 1, you consider this. This is less than or equal to norm x. So there is no x here. See, I'm doing this because you have to be careful when you take supremum, when you work with supremum and infimum. For any norm x less than or equal to 0, norm of tx plus sx is less than or equal to this. This is the triangle inequality in the Banach space. So this is the definition of the norm. This is less than or equal to norm t plus norm s. Okay. So now there is no x here. So all these things, this is true for all x. So then you can take the supremum here. Okay. Then now you can take the supremum here. Norm x less than or equal to 1. So that is equal to norm t plus s. Okay. That is equal to norm t plus s. Okay. Just to be careful, I have done all these things. Now we want to prove it's a Banach space. Okay. So to prove. Yes, you want to ask something? And this is complete. Did I record? Yeah, I think so. Suppose Tn contained in B of xy is Cauchy. Okay. Then we want to find a limit in this. We are assuming y is complete. Okay. Assume y is complete. Then Tn, we are assuming y is complete. Is complete if y is complete. Okay. This means that Tn minus Tm goes to 0. This norm as n and m goes to infinity. Okay. This implies for all x in x, Tnx, Tn minus Tmx, which is Tnx minus Tmx, right? Because it's linear, goes to 0 as n and m goes to infinity. Okay. Now this is in y. Since y is complete, Tnx converges to some y in y. Okay. Now you define T of x equal to y. This is of course well defined. There is no well definedness problem. This is clear. Okay. And T is linear because Tx equal to limit of T and x. Okay. So if you insert an alpha here, you will get an alpha here. Then the limit, since we have already seen that the scalar multiplication, sum, all those things are continuous. Because of that, you can play with the limit. You can take the limit inside the addition, inside the scalar multiplication, all that. So we have already seen all those things. So because of that, we know that T is linear. Okay, we are using the fact that scalar multiplication, addition are continuous. Okay, and each Tn is linear. Because each Tn is linear, Tx is linear. So we got a linear map which is which has a point-wise convergence, okay, property. We have to do two more things now. We want to verify, we have verified T is linear. We want to verify that T is bounded and that T converges in that norm, in that operator norm, because we want to show that B of xy is a Banach space with respect to that norm. So here we only have point-wise convergence. We want to prove that it converges in that operator norm. Okay. First, we have to prove that it is bounded. Tx is less than or equal to T minus Tnx plus norm Tnx, right? So I mean, I can do this. I can write this is okay. Do you mind it? It's okay. The norm is continuous. Norm itself is continuous. So Tnx converges to Tn. So I can just limit n. I can write it like this. Okay. Now I can choose Tn. See, Tn minus Tm goes to 0 as n goes to infinity. Okay. This is true. This is true for all n. I'm taking the limit in n only, but this is true for all n. Now Tn minus Tm goes to 0. So choose n such that Tn minus Tm, this norm is less than epsilon for all n and m greater than m. Okay, choose m. Okay. What I'm saying is this norm Tx will be less than epsilon plus norm Tn. Epsilon times norm x. I mean, this will be less than norm. This is less than norm Tn minus Tm times norm x plus norm Tm times norm x. Right? Right? I'm just using the norm inequality. Because of that, this will be epsilon times Tx norm Tm times norm x. So it's bounded. M is some fixed m. Okay. Choose m greater than or equal to n. Okay. So that this is less than or equal to n. Okay. This is clear? If not, you ask me. I mean, you have to write carefully the epsilon and other thing. But it's okay.
Yeah.
Okay, I assume it's okay. If not, you tell me. Okay. Okay, so T is bounded. That is clear. Okay. I mean, T is bounded. That is, this norm T is less than or equal to epsilon plus norm Tm. Okay, for some m, which we can fix. Okay. Okay, now we want to prove T minus Tn goes to 0. Okay. So this is what we want to prove. Okay. Now T minus Tn x. Okay. Okay. This is equal to limit Tn minus maybe m Tm minus Tn x. Okay. This is less than or equal to limit of Tm minus Tn I mean, this is less than or equal to, I just don't want this norm of this. This limit is in m. Okay. For all x, this is true. Right? Now you take the supremum here. I'm assuming norm x is less than or equal to 1, then I got this inequality. Okay, then you take the supremum here. That should go to 0. Is this fine? Is it okay?
Okay.
Okay. If not, think about it. If there is a problem, raise it in the next class. Okay. So see you. Okay. I will end the session.
Okay, sir.
Okay. Thank you. I don't see the end.
Thank you, sir.
Okay.